Testing. Hello, welcome to, well, in spite of Netcraft confirming that OpenBSD is dying, we now have Peter Hessler presenting about bidirectional forward detection in OpenBSD. Thank you.
All right, thank you. So my name is Peter Hessler, and I'm with the OpenBSD project. Recently I've been working on implementing the BFD protocol within OpenBSD. So first we'll give some background of what the problem space is and what we're trying to do with it. So routing is simply the delivery of packets. Routers know only what the next place to send the packets for. So that way when you go from A to B, each router along the path does its own lookup and makes its own decisions based on that. So how does we do this? We look up the destination. We go through the fib, which is the installed and functional routing table, and we make a decision. And one of the decisions on whether or not we can utilize a route is whether or not it's up and marked as usable. So traditionally within a BSD-based Unix system, this is a flag that's on each of the routes, RTF up, for example. So before BFD, you would monitor the link state of the interface that the route goes over. It's not really reliable. You can guarantee if the link state is down, then it's not usable. But conversely, just because the interface is up doesn't mean you can actually send traffic across it. There can be active devices between you and the neighbor that you want to actually send the package through. Sometimes there's a switch, like for example, if you're in an IXP, there can be long-reach connect equipment. There can be a variety of different things that can block the link state from being directly visible. In addition, there are various failure modes where the device still has power and still has either the copper signaling or the fiber optic signaling coming across, but it's just not capable of actually forwarding packets. So in BFD, it's traditionally used on large routers. And in large routers, you use a variety of protocols to decide or to learn the routes from your neighbor. Traditionally, BGP is the most commonly used one. The default timers on that can be pretty long. 90 seconds is an eternity before you can discover an outage. How much traffic is that if it's 10 gigs? 100 gigs. You know, if your CEO is using your voice over IP, 90 seconds of dead airtime means the CEO is going to be very unhappy, and you might need to update your CV for that. And the way BGP is standardized, the fastest possible that you can do is 3 seconds before detecting an outage. That's also pretty long, and many larger routing implementations simply cannot handle sending the keep alives that fast. And it's a lot of extra packets on the wire. OSPF, LDP, all the other protocols also have their own built-in keep alive mechanisms, and that all adds up. If each one has to discover independently whether the link is valid or invalid, you know, each one starts sending a packet every second, and if you're running, say, 4 protocols, that's guaranteed 4 packets for every periodic that you want to check the health. So that brings us to bidirectional forwarding detection. There are 2 very important RFCs that describe this. The first one is RFC 5880, and it describes the actual protocol itself. It stands for bidirectional forwarding detection, and it sends a packet to the remote machine. The remote machine processes it and sends a response back. And so that checks both sides of the link. And then the other side will also run its own BFD against you. So it sends and it receives. It's your basic keep alive mechanism, sending and receiving packets. ping is a very simple example of how this works. And it's protocol independent. You can encode BFD packets inside of any sort of container format that you want. So the other standard that's really important is 5881, which is BFD for IPv4 or IPv6, and it's just your basic UDP packet. This is just probably the most common way of doing it. You can also embed BFD packets inside of OSPF with an LDP, monitor, MPLS. You can do it on an LACP trunk for each of the links in the trunk to specifically monitor those. But we won't be getting into that. We'll just be talking about the basic standard mechanism. So, as I said, what is BFD? It's pretty commonly found on big iron hardware, large routers, 100 gigabit and faster. Pretty commonly used with BGP and MPLS in your standard, either internal routing or external routing. In the standard, as I mentioned for BGP, it uses just integer seconds. And so you're limited to how often you can send and receive these packets and what your detection rate is. In BFD, it uses microseconds, which is 1,000,000 times per second. So you can have incredibly precise timers on this. As an implementation detail for OpenBSD, we still have a tick in the kernel. And so I've decided, just pulling a number out of the air, that we won't support faster than 50 milliseconds. Implementation detail should be easy to change if we decide we need faster resolution. So there's two main modes within BFD. There's async, which is just traditional, keep alive. You keep sending packets, you keep receiving packets. If you lose them, you go through the error handling case. If you lose 3 in a row, you just mark it as down, and you bring down the session. There's also a really clever mode called demand mode. And the specs says deciding when to send a packet is undefined. This is implementation specific. The vast majority of them are using this based on the traffic counters. If I've received a packet from my neighbor, I know my neighbor is still up. And so I can just receive the packets and just monitor that. And if I haven't received any packets for, let's say, 100 milliseconds, then I send a health check. Are you still there? And then I just send the normal async packet. And I get the response, and everything's good. There's some interesting parts to the standards. You can definitely tell what types of people were involved in writing the standard. In this case, I'm pretty certain it was a hardware engineer who decided this. So this is a direct copy of section 4 from the RSC itself. I've highlighted the interesting parts in bold. So you see that the source port must be within a certain range. Normally for TCP or UDP, no one cares what the source port is at all. Apparently this one does. So it must be in the upper range, 49.152 through 65535. The source port should be unique across the entire system for all of your neighbors you've configured. This just screams that it was a hardware engineer who decided, okay, it just takes 2 or 3 pins just to detect this, so let's make it easy. You should minimize how many times you repeat this, but ultimately you completely ignore this, and you must use the actual way that's built into the standard to decide which your neighbor is. So we have all these ideas and then we ignore them. Which then brings us to how we actually define who our neighbor is. And essentially that's used in this discriminator field. It's a 32-bit integer. You put in whatever you want. You're supposed to keep it static, and the responder just copies that into a field and says, this is who you are. So this is how you figure out who you're receiving the information from. You can change it. And what that means is completely up to the implementations. So again, we made a thing and then completely ignore it. It has a section that's euphemistically called authentication, a way to prevent replay attacks, to verify that the BFD packets you're receiving are actually from the neighbor that you think you're receiving them from. Because as we all know, spoofing an IP address or a MAC address is incredibly difficult and just really, really hard for a lot of people to do. So in the various authentication sections, there's the type, the length, a serial number, which you generally want to increment, and then the crypto payload. And there's, for each of the different authentication types, for basically the different hashes that are used on this, there's the keyed and meticulously keyed. And in meticulously keyed, the difference is that you must increment the serial number for every packet you send. Which means that the non-meticulously keyed completely ignores the replay attack problem, and you can just keep sending the packets as much as you want. And interestingly, SHA-1 is the strongest hash that is standardized and is supported. You have raw plain text, which is completely utterly useless. You have MD5, which lol MD5, and then you also have SHA-1, which kind of was okay, but now is relatively easy to break. So what is the status of this? This code has been committed to OpenBSD. It is available within the system. I've implemented all of the musts. It's currently still a minimalist implementation. I have in my lab a Juniper MX80, and that's the non-me device that I've been developing against primarily. I've had a lot of other people test it against other hardware, Cisco, Brocades, Extremes, a few others that I'm just not remembering right now. Each of them have been tested for at least 5 days each. I think in my test lab, I got up to 3 months, and then I changed something in the kernel, so I had to reboot again. It has all the basic things you want. It has logging. Inside of the BSDs, we have what's called route messages. And this is the kernel routing framework, is just sending messages to userland saying, for example, we have a new interface. The interface lost or gained link, or a new IP address showed up, or a variety of other things. Anything that's interesting to routing or IP addresses. And so I've implemented a BFD-specific message on state transitions, going, oh, when we came up, here's some details on it. Oh, we came down, here's some details. So applications in userland can make a decision on whether or not they want to do something special for it. Your BGP daemon, for example, may be interested in changing the state of the neighbor, or doing an early reroute before the neighbor pulls its state, for example. And it also just shows up as just normal IP packet. So you can block it with PF, which is the firewall built into OpenBSD, and you can do any of the normal tricks that you would want. Configuration is via the route command. Since this is based on routing and everything is configured on the next hop, it completely makes sense. This stays within the family very nicely. Due to how the BSD routing code is kind of, this aspect of it has rotted a little bit over the years. So the up and down flag is basically completely ignored in half of the routing table. So unfortunately, changing that doesn't do much. So we'll have to fix the whole routing subsystem to understand that before we can trustworthily enable that. That would be very nice to handle the static configuration case, where if you just want to monitor just a single next hop, you have a couple static routes going over there. That would be very nice. So for now, the special route message is how you communicate with daemons to decide what to do. Currently within OpenBGPD, it understands the messages and is able to mark the next hop as invalid, which triggers the standard BGP routing decision process to move routes off of that or onto it when the neighbor is marked as BFD up again. And because it's configured based on a route and not on the interface itself, this works really well for if you want to have multiple neighbors you want to monitor going over the same interface, which is a pretty standard configuration at an IXP. You plug into the IXP, you do BFD against say, for example, the route servers, or against a few neighbors that you strongly want to keep up as much as possible because you send them a lot of traffic. This way you can monitor each of them independently from each other, and you don't have to enable it on all of them. So you can selectively bring them up and down based on how much, whether or not you lose the BFDs. So this is just a very simple way to configure it. So you see here we have the route command. We're going to change for this neighbor, and we're just going to add the BFD flag. So what that does is that just tells the implementation to start BFD, start sending the health packets, and then let BFD itself make various decisions. So you see here in the second command, you see the capital F for BFDs is involved. This is just, we have a command called route get. This gets information and just prints all the stuff. So you see here in the BFD section, it tells you all the stats, you know, what mode is it in, the various states, the various internal information. I think probably the most important one is the state up. You want to know the discriminator and the remote discriminator and the uptime. Those are probably your most important fields, but these are all the fields that BFD sends across to each other, so you can use that to analyze and make your own decisions. This is a command called route monitor, which just monitors and just prints out any of the routing messages that we receive. And you can see that this is pretty much the same information that you're getting from route get. This is what your applications would have available to them to make decisions if they're listening to the routing socket. This is the neighboring device. This is just an example of what the Juniper that I have in my lab sees. If you use BFD within Juniper, this is all pretty self-explanatory. And if you haven't, you have the state is up there on top, the remote state, and then you have the discriminators down here. So that's what I have working right now. There is still quite a bit of work to do for the future. Actual manipulation of the routes up and down states would be a fantastic thing to do. That's sadly more of a long-term plan than a short-term plan. As much as I like to make fun of the authentication support, we probably should add it because a number of neighbors will want it and they will require this support, and not implementing it will just make it more difficult to deploy in the wild, and that's probably a bad thing. We want to make it as easy to use and as straightforward to use as possible. There's a updated RFC called Seamless BFD, which at a close glance, it looks like they solved a lot of the original design issues with BFD. And so that would be kind of a BFD version 2.0, and that would be really nice to support as well. But there isn't a lot of, but Seamless BFD has not yet been deployed into the wild. It's not yet in the standard software images for other router vendors, so it's not a huge priority to push that out. Multipath support would be very nice as well. Multipath Multi-Hop. So original BFD is only for the single directly connected neighbor. Multipath and multi-hop allow you to monitor device that is farther away, and you can specify which of the various routes that you're taking to it. So you can go, okay, well, I want to monitor BFD multi-hop to 8.8.8.8, the Google DNS cache, and then you monitor, okay, well, going over this uplink or this uplink or this uplink, and you monitor all three of them, and then you can decide, and then your system can decide based on a variety of characteristics which ones are valid and invalid. Yeah, so because we are not actually manipulating the up and down state, and because a lot of the routing daemons really want a lot more, can really utilize the information that BFD is monitoring for their neighbors, we want to add more specific knowledge into the various routing daemons. Of course, BGP, as I mentioned, LDP, which is our label distribution protocol implementation for MPLS. We have OSPF, EIGRP, quite a few other standards, other implementations. There is an implementation of BFD for OSPF itself, where you send it as just OSPF payload. So that could be interesting to kind of look at and to see, how commonly used is that? Does it make sense for us to add it directly into the OSPF protocol? I think adding it to LDP specifically to monitor the MPLS neighbors, that would be very beneficial as well. VXLAN, of course, can get this. You can encode the BFD inside VXLAN packets. We have a implementation of OpenFlow 1.3 something or other, and that is in SwitchD. So it'd be very helpful for us to add that inside our OpenFlow implementation, so we can just use OpenFlow decision processes. And there is a very nice draft, which looks like it was just resurrected last week, partially written by DKNOG, that allows BGP implementation to send a message to a route server at an IXP. And the route server tells all of its neighbors, hey, router A supports BFD on it. And so when you support BFD and a neighbor who is directly accessible via Nexthop, but who you don't have a special BGP session set up, you both see this, and you build the BFD session to each other automatically, and then so you get the automatic checking, and then only after BFD is declared these sessions to be healthy, then you start installing routes on it. That completely removes one of the major failure modes that an IXP can have, where the control plane is still up, but the data plane is not accessible. And this draft is what got me very excited about BFD to begin with, and got me started to looking at this. So I'm very happy to see that the idea is being resurrected, and I will definitely be looking at this in the future, and hopefully working with the authors on making sure it's a very strong RFC. And so, since I am talking quickly, and I generally give this to sysadmins and developers, so I have spent a lot more time explaining networking. So I am done. Does anyone have any questions?
Yeah, I was thinking two things with regards to RelayD. We are using that for doing routing failover. Do you think this will be implemented with BFD also, or can it be incorporated?
Yes. So to give a little bit of background for those in the audience who aren't very familiar with RelayD, RelayD is basically a health check mechanism that will install either specialized rules in the firewall for layer 4 Layer 4, it can do layer 7 itself, so that includes like SSL termination and things like that, or it can also do health checks and install routes. So a common case would be you just do a ping against your 2 various gateways and you decide which one's active based on who is up. So that's really kind of popular for your small home, small office kind of setup. And yeah, so adding that sort of integration into RelayD could be very helpful as well. Yeah, sure.
Also for application servers, I would think it would be nice if you could check your application servers and have very quick disabling like app servers behind the RelayD. That would also be...
Yes, exactly. So you can also use it on the layer 4 or the layer 7 modes to go, oh, my backend application server is not responding in time, so we bring it down much faster than the normal health checks. Because again, with trying to do your health checks in various other protocols, they're slow. They're slow to detect failure. And so BFD, we want to make it detect failure as fast as possible so we can take out things that are degraded out of the network.
Another question. When the BFD decides to say, okay, I will remove this link, will it, can it be set up so I will inform my neighbor that I have decided to make you unusable? So if the neighbor means he's still alive, he can send a new BFD hello package so I can see the link is should be alive.
Yes, so when you change state from up to down, you send immediately a packet to your neighbor saying, I think you're down, and then there's a few sub codes of why you think that they're down. And then periodically you just send a health check, are you there yet? And that also includes the, I think you're down for this reason.
Yeah, okay.
Yeah.
Yeah, this is functionality I've been used to. I'm an old PDH, SDH guy, so therefore I'm used to all that kind of mechanisms. And yeah, they're still coming into the Ethernet world.
Yeah, exactly, yeah.
Arnold Nippert from DKNOG. So thank you very much, Peter. Yep. From a practical point of view, you said the timer might be as little as in microseconds, your implementation as down to 50 milliseconds.
Yes.
Practically, how many BFD sessions am I able to run on a typical machine? Do you have any experience in that? How much load does the single session put on?
It is unmeasurable. I've had 1,000 sessions on it, and it's maybe 1% of CPU time. Okay. And most of that is just due to how the kernel switches between tasks.
So, for example, for IXPs running route service, you would recommend also to provide BFD then?
Absolutely. Absolutely. Because, so your traditional case of just a single cable between 2 routers, that's relatively reliable. We understand that really well. Detecting failures is relatively straightforward. In an IXP case, you're practically guaranteed that your neighbor is going to be on a different switch than what you're on. And so you have all these multiple components involved. You have multiple physical links between them. Depending on how the IXP is built, it can be, tens of kilometers apart from each other, and you can have like up to like probably 10 active devices in the chain. So having BFD doing the health check there is really beneficial to guarantee that the link is up. And as I said before, the data plane and control plane separation that is inherent with a BGP route server is dangerous. There have been major outages in the past. I've been told that failure mode is the reason why several large organizations will never use a route server, and they always manually configure all of their neighbors. But in my day job, I work for a medium-sized data center. Route servers are incredibly beneficial to us because doing peering is only part of my job. I also have to run the actual network as well. And so getting neighbors just to pop up automatically is fantastic. And if they can do health checks automatically against each other, that is also very beneficial. Then I don't have to worry about, oh, there was a link failure somewhere, but I think they're still up. And just being able to kind of let the network heal itself quickly is really beneficial.
Is that a follow-up to the same one? Is it a follow-up to this one? No. Okay.
Okay.
Okay, hi Peter. This looks really interesting. I have maybe a hard question for you, because when is this actually going to come in the stable version of OpenBSD? When can I actually use it?
So we are in the process of finishing up the 6.1 release. There has been quite a large number of changes to the network stack. We're making it basically SMP safe. Unfortunately, one of the mechanisms that I'm using to receive the data is very complicated to change to be SMP safe itself. And so unfortunately, we've had to disable one of the things that I depend on. So we will not be able to have BFD enabled for the 6.1 release. I am really hoping that we can have it enabled for the 6.2 release, which will be, the tentative schedule is November. But that being said, I have this in use both in my lab and in production, and so I have turned that back on, and I haven't seen any ill effects. But as a developer, I'm working closely with the other developers in the networking area to verify that there won't be any issues with that.
So if I understand it right, if you, for example, have multiple interfaces between you and your neighbor, BFD will only use one interface. For example, if I have a bundle, it will still use the same port.
Correct, yes.
So LSCP, of course, helps and detects when some link in this bundle fails. But what is if I have set it up statically? So BFD will still perhaps say everything is good, although one of the links may also only go in one direction. Does BFD provide a solution for that as well?
Yes, so there's two methods of doing BFD over bonded links, and one of them is just send it as normal IP traffic. And so whatever your normal IP behavior would be, and yeah, in this case, you just send it over the top, and that's one method. The other method is you can actually send BFD inside LACP packets themselves. So each member of that bonding, they send their own BFDs, and so you can do health checks on each of the members, and then tear down just that one link from the trunk.
Any other questions? All right, well, thank you very much to Peter. Could we give him an applause?